Hello. In this video, we want to discuss the concept of equivalent relation as well as equivalent class. So with this example, we shall buttress what equivalent relation mean and what equivalent class mean. Now, let's look at this example. We are told that a relation A congruent B modulo 5 be defined by A minus B is equals to K dot 5, where A, B, and K are integers. Then show that the relation is an equivalent relation. We want to show that this relation is an equivalent relation. First of all, before we go to solve this problem, we have to recall the definition of equivalent relation. What is an equivalent relation, or when is a relation said to be equivalent? Now, an equivalent relation is a relation that is reflexive, symmetric, and transitive. Fine. For a relation to be equivalent, those three conditions must be satisfied. So now, we are given that we should show that this A congruent B modulo 5 is an equivalent relation. To start with, for it to be reflexive, we want to show for first to show reflexive relation. We need only one element. And what is the element? Now we have the elements to be A, B, K, and Z. They are integers. So let's pick A. No. Now we define as, because we are told that what we want to show is that A congruent, A mod 5. Yes, A congruent A mod 5. How do we define that? That implies A minus A, because B will represent A now, because it has to be reflexive. So A will be A. And A minus A is what? 0, which is the same thing as what? K. Our K here is 0.5. You can write 5.0. We are multiplying anyway. It's not decimal point. It's 0 multiplied by 5. So which implies invariably comes back to this means, because A minus A now is 0.5. So which means 0 is what? Is our K from this definition, and 5 is still 5. Okay, so that means this has satisfied the fact that A mod A, and it's A congruent A mod 5. That is just as simple as that for reflexive relation. Don't forget our A is coming from integers. Okay, now to show what? To show the next one is to show symmetric relation. Symmetric relation. How do we go about that? We need two elements here. We need two elements. First of all, we have the definition should be what? A congruent B modulo 5. Fine. Now, we know that since A minus B, is equal to what? Is equal to K dot 5. We know that, sure, by our definition. Now, suppose we now want to have, when you say symmetric, it means the other side of it. If we turn it the other side, the other way around now, this is, we know this is sure. Now, if we want to turn this the other way around, it will be minus B plus A, minus B before plus A. Now, which will be the same as what? Minus, you extract minus out, then you factor out my minus. So we have minus into bracket B minus A. Okay, this gives us minus B plus A. Fine. So let's continue up here. Let's continue up here. Let's continue up here. Now, since we are having minus into bracket B minus A now, and remember when it is A minus B, we have K dot 5. Now that we are having negative sign here, so for us to write it in tandem with K dot 5, it will not be what? It will not be minus into, let's write that, minus into, B, for you to see clearly, think this is not clear, minus into B minus A is what? Is equals to K dot 5. It will not be K dot 5 like that. Why? Because this minus means the K will be affected. And don't forget, K is an integer. So this now imply what? Minus into B minus A is equals to minus K dot 5. Yes. That's minus K dot 5. Okay. And now you can see that multiplying these two sides by minus, K assume minus sign. So which implies, and you know that minus K is an integer, because integer can be what? Negative, can be positive. So now that implies, if you look at it holistically, you will now see that You now see that. This one now, which is now invariably, don't forget this minus disappear as soon as you multiply by high. Good. So that implies now what, that a minus b, which is k dot 5, now is equivalent to b minus a, which is minus k dot 5. You understand? Yes. Simply because k is an integer, minus k is an integer. So we could now say that the hence a congruent b modulo 5 is the same thing as b congruent a modulo 5. That's it. Because it has given us the same pattern what we are looking for. Now that is how to get to prove symmetricity in this relation. Now how do we now prove for the last one, which is transitivity? Let's see how we want to prove. To show transitivity, let's A, B, C, be integers. Let they be integers. Fine. So that means that we can have what? A congruent B mod 5, and C congruent, or say, sorry, B congruent C mod 5. How? Let's go there. Okay. Now let A congruent B mod 5 be defined as A minus B is equals to K1 dot 5. Yes. How? What do I mean? Fine. I'm using K1 now because I will use another K here. So to distinguish one K from the other, we need K1. From the basic definition, it is K. But now, since we want to combine two things together, two relations together, we need to differentiate one K from the other. Okay, fine. So similarly, B congruent C mod 5 will be defined as, we imply B minus C equals to K2 dot 5. That is what? Equation 2. Fine. Now, adding equation 1 and 2 together. Let's add the two equations together. Well, let's add it together. Adding 1 and 2. Okay. Adding 1 and 2 gives, you're having what? A minus B. It's got what? K1 dot 5 plus B minus C is equal to what? K2 dot 5. Good. Now add the left together and add the right together. You add left, you add right. Okay, what do we have? What do we have there? So the left here is A minus B plus the left here is B minus C equals to what? K1 dot 5 plus the right here K2 dot 5. Okay, so which will be equals to what? If we add this thing together, A minus B plus B minus C will be equals to what? K1 dot 5 plus K2 dot 5. I hope that is clear. Okay, now, so which invariably will mean, you can have minus B plus B cancelled. You have A minus C is now equal to what? K1 dot 5 plus K2 dot 5, which implies A minus C equals to what? K1 plus K2 dot 5. Yes, because dot 5 is common. We factor it out. So we can now write that A minus C is equals to what? K, dot 5, where K is equals to K1 plus K2. Okay. So invariably now, you have shown that, which means that A minus C is obtained from what? Is obtained from A. That implies that this implies A, is equal to C, oh sorry, A congruent C mod what? Mod 5. A congruent C mod 5. You can imagine, you observed clearly that what? This relation has exhibited that it is what? It is reflexive because it satisfies that condition. It is symmetric, and at the same time, it is transitive. From moving from A to B and B to C has given us that the pattern of that particular operation or relation. So this is the conclusion of how to show that the relation is actually what? Is actually reflexive, is actually symmetric, is actually transitive, which is what altogether the relation is equivalence. Now, having done this, let's now look at the equivalent class. Let's look at equivalent class. What do you mean by equivalent class? Fine. What do you mean by equivalent class? To us to define equivalent class, let's pick A, for example. And how do we find A? A can be a set of, let's say, X such that X congruent A mod 5. This is a set, okay? Another class is a set. So which can be also defined further as X such that X minus A is equals to K dot 5. K is an integer. Don't forget that. Fine. Which can be also further extended as X such that X is equal to, taking A here, become plus A plus, you have what? K dot 5. Are we together? Fine. So K is still what? Is still an integer. Now, for us to show, as far as that question is concerned, our A will be, let A be equals to 0, 1, 2, 3, and 4. We will not include 5 because the modular mathematics there is having a 5. So it will stop at 4. And our K, and let K, since it's what? It's an integer, it could be what? It could be 0, it could be minus 1, it could be minus 2, it could be minus 3, it could be minus 4, it could be, minus, and so on. And it's also it will be 0, 1, 2, 3, 4, and so on. Okay, K can be extended, K can be varied, but our A will be between 0 and 4. Now, what am I saying? What do I mean by this? Let's use one as an example first. Now, the equivalent class of 0. How do we define the equivalent class of 0? Don't forget we said you are going to see where we're going to get there now. Now, our A is what? Is 0. So we can say that will be 0 plus, you can start from negative sign if you like and go further. Okay, let's say our K is minus 1. Minus 1 dot 5. That will be what? That is what? 0 minus 5. That is minus 5. Beautiful. Beautiful. So if we have, again, you can see how when we vary K, 0 plus minus 2 dot 5. That is 0 minus 10. That's minus 10. Okay, 0 plus minus 3 dot 5. That what? 0 minus 15. That's minus 15. I hope you are getting this logic. So you can continue on and on like that. Well, yes. Just continue. 0 is equal to, 0 plus minus 4 dot 5. You can have what? 0 minus 20. That's minus 20. So we get on and on. Let's try the positive side of our K when K is now positive. Okay, let's check. Let's K now when K is now 0 and so on and so forth. So we have what? When K is 0. No, that way when K is 0, 1, 2, 3, and so on. It can be 5, just and so on. Oh yeah, let's write. So we have, we have what? The equivalent class for 0 there is 0A plus 0 dot 5. That will be 0 plus 0 is 0. Yes, from our definition. Then 0 plus K, now it's now 1 dot 5. That will be 0 plus 5. That will be 5. We are multiplying 1 times 5. Okay. So when is what? Let's write further. Now, when it's what? When k is now 2, 2.5, that's what? 0 plus 10. You can see that it's 10. So if you observe closely, you will see that there's difference of 5 from one element of the class to the other. Okay. So now, without wasting our time, because the pattern is just like that, on and on. So we now say that, therefore, the equivalent class for 0 will have so many elements, which you cannot list them all. So with minus 15, as we have calculated, comma, minus 10, minus 5, 0, 5, 10, 15, and so on. It will have both positive and negative values because k is an integer. That is that about that. Now let's look at the next one, 1, equivalent class of 1. I will do 1 and 2 for you. You will finish the other ones yourself. Okay? Now let's do for 1. Make a class of 1. Remember, or should I recall that? Let's recall that we define our x as x plus a plus so our x now is 1 plus. If we use negative sign, our k, like I told you, start from 0, okay? But now it's not 0 here, okay? Sorry, our a is 1. These are 1. K can be what? 0. Thank you. 0.5. That'll be 1 plus 0. That'll be 1. Beautiful. Now, a will be consistent. 1 plus, the k will be changing. 1.5. We are multiplying. Don't forget, it's 1 plus 5. That is 6. Beautiful. I can have what? 1 plus k changes to 2.5. That is 1 plus what? Plus 10. That is 11. Okay? I hope that is clear. Good. Now, let's suppose we use the negative sign of k, because this one will be on and on, and this one will be increasing like that. Let's look at the negative sign of k. So we have 1 plus minus 1 dot k. Yes. Now, k is minus 1 here. You can't use k is equal to 0 again because we have used 0. So that will be what? 1 plus times minus is minus 5. That's minus 4. Good. When k is what? Minus 2. Dot 5. That will be what? 1 minus 2 times 5. That's minus 10. That's minus 9. You see that the numbers are different. One is different from the other by 9. So because we are operating on mode 9. Is that clear? I'm sorry, we are operating on mode 5. So in this case now, our equivalent class for 1 will be, if you continue like that, the next one will be what? If you look at it now for the pattern, the next one will be what? Minus 14. The next one will be minus 19. Here's it now. Just be adding negative sign to it now. Minus 4, minus 5, minus 9. Minus 9, minus 5, minus 14. So we can have dot, 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 comma, minus 14. Don't forget, this is minus 15. Oh. It's not ordinary 15 because it's negative. It's on the negative side. Minus 14, minus 9, minus 4. What next here? After, if you had minus 4 to 5, that is 1. You first add 1 for the negative, for the positive side. We have 6. We have 11. We have 14. 11 plus 5, that will be 16. Thank you. Then come dot, 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 and so on. That also applies to that. I hope you get it now. So looking at each element in the class are equivalent, but no two classes are no two classes have the same elements. No. You can never see in an equivalent class that one class we intercept the other class. No two classes in an equivalent class will have the same element, and at the same time, each element in each class will be equivalent. Minus 14 is equivalent to minus 9. Minus 9 is equivalent to minus 4. So they are all equivalent. But that the elements you have in equivalent class of 0 and equivalent class of 1, we have the same value. No, you can never get that. You can't get that. Okay? I believe you can do the other ones yourself by picking up 2. Use this pattern that I've explained to get the answers to equivalent class of 2, equivalent class of 3, and equivalent class of 4. So I'm giving you that as an assignment, which I expect you to submit in the comment section. If you understand and enjoy this video very well, and you are watching us for the first time, I want you to subscribe and click the notification bell so that each time I upload a video, you'll be duly informed. At the same time, don't hesitate to like, comment, and share this video. God bless you. Bye.